Thank you. What if I told you that your own brain probably holds the next secrets to the next generation of optical imaging? Right now, your eyes are not capturing everything around you. Instead, it focuses only on changes, movement, and new informations. So if you don't shift your gaze, or if there's nothing moves, your brain is not actually processing. What you see right now is simply a view that reconstructed moments ago. In this way, your brain saves a lot of energy and can process information with very low latency and bandwidth. Now, imagine applying the same intelligence to machines. Could we build a vision system that, like our brain, focus only on what matters? This is exactly what we have been researching, a completely brain-inspired optical imaging system that can see through obscured environment, such as fog, smoke, or human tissues. The world's first X-ray image was taken in 1895 by William Rogan. It paved the way of what we know today as medical imaging, which helps physicians to diagnose patients without surgery. Very helpful, but it is based on ionizing radiation, so it could be potentially cause damage. Visible light exists everywhere in our daily life. It is safe and can penetrate pretty deep inside our body. For example, if I use my flashlight of my cell phone to put it on my palm, you can see it coming through from the other side. The reason why we couldn't see the structural information, such as bone, vessels, is because of photon scattering problem. Photon bounces towards different directions while propagating inside our tissues. That's losing information. So to solve this, our brain-like imaging system leverage attention, memory, and most importantly, spikes to reconstruct, to address this problem. The imaging system includes three major components. First, the bio-inspired digital eyes, a deep spiking neural network, and a neuromorphic processor. So at the front end, we use dynamic vision sensor, a camera that just works as our retina. It only reacts to changes. Each pixel of the camera can convert the analog optic signals into digital spikes, just mimicking how our retina cell fires. But detect changes is not enough. To understand the scene and reconstruct the hidden object, we also need intelligence. That's where spiking neural network comes in. It mimics the realistic neural connections inside our visual cortex. And it can be programmed and designed and use its intrinsic ability to process those accumulated spiking informations. The last part is neuromorphic processor. It is new computing hardware, not like a CPU or GPU. It is a new architecture that consists by millions of electronic neurons. And those neurons can be reprogrammed and configured to run spiking neural network and process spiking information just like our brain cortex. So here in our benchtop experiment at Brown, we put different kinds of unknown objects behind artificially made scattering medium, such as fog and turbid water. And our imaging system, and we let the target move actually randomly at high speed. Our imaging system has demonstrated it can both track and reconstruct the object accurately at high temporal resolution. So the ability to turn invisible into visible has profound real-world applications, such as in autonomous driving. It can help the driver and vehicles to detect the incoming cars and pedestrians in severe weather conditions. Another example in disaster response. It can help firefighters to see through smoke, potentially saving lives. In biomedical imaging, it has the potential to non-invasively visualize brain activities and detect tumor to enhance healthcare. So by applying the brain-inspired sensing and computing together to address our real-world imaging challenges, my research aims to push the boundary of what we can perceive to improve safety, healthcare, and beyond. Thank you so much.